Your brain is physically three-dimensional, but describing its complicated web of connections might require that we study the mathematics of structures in 11 dimensions. In order to dive deeper into an exciting topic, we're mixing up the format. Over the next 3 days, we'll spend 3 episodes exploring an incredible application of seemingly purely abstract mathematics. How algebraic topology can help us decode the connections among neurons in our brains to help us understand their function. If you were to watch a brain think, you would see a beautiful mess of activity with neurons firing all over the place. This wild world must have some order. But coming up with a precise and quantitative description of that order, of how the brain is processing information, is extremely difficult. Being a mathematician, I'm predisposed to think of scientific concepts in overly simplistic ways. Applied mathematics is often about finding the correct framework, a sort of essential structure for a problem, and ignoring the details. So, how should a mathematician view a brain? Basically as a graph. Not a graph like y equals mx plus b, but a graph in the sense of a collection of vertices, or nodes, connected by edges. The graph will represent the connections among neurons, the activity of the brain, over a little time slice. Each neuron is a vertex. If, during our little time slice, there is an active connection between 2 neurons, connect their representative vertices by an edge. That's the neural network. There's a big question in neuroscience about how to analyze the structure of a neural network. Let's say you're moving your right pinky finger during that time slice. How can we read or interpret that action, which is the functional outcome of your neural network, from its structure? It just looks like a big mess of vertices and edges. Well, to approach this problem, the first thing we need is a neural network to study, an actual brain, or at least a model of one. This is where the Blue Brain project enters the picture. Led by neuroscientist Henry Markram, the goal of the Blue Brain project is to create a digital reconstruction and simulation of the brain. Using a complicated algorithm that accounts for decades of neuroscience research and biological principles, and then testing it against real brains, the project built, quote, digital reconstructions of rat neocortical microcircuitry that closely resemble the biological tissue in terms of the numbers, types, and densities of neurons and their synaptic connectivity. This digital brain has roughly 31,000 neurons, or vertices in the case of the graph model, and 8 million connections, or edges. There are serious neuroscientific questions about the legitimacy or accuracy of this reconstructed brain. It's controversial, but that's a question for neuroscientists. As applied mathematicians, we'll work with the data given. The neuroscientific problem is to construct a graph showing the connections between neurons, and the mathematical problem is to analyze that data. No doubt, these are related questions and should be pursued in tandem, but we'll focus on the second part. So, here's our challenge as mathematicians. We have a bunch of huge graphs, each of which represents the connections between neurons within a given time slice. How do we extract useful information from this? A lot of the analysis of graphs, or networks, suffers from a local versus global problem. One can study local properties of a graph, like the degree of a vertex, which is the number of edges connected to that vertex, or global properties, like the average path length to get from one vertex to another. But knowing only local or only global information about a graph generally can't tell you about its entire structure. For example, these 2 graphs have the same average path length, but they look completely different. The tools of algebraic topology are uniquely equipped to provide quantitative information about both the local and global properties of a graph. Driven by this insight, a recent paper from Markram and mathematicians Catherine Hess and Ron Levy interpreted these graphs as directed simplicial complexes, a common object of study in algebraic topology. And that framework has been fruitful, revealing high-dimensional structures that were previously hidden. So what is a simplicial complex? We'll dive into the abstract world of algebraic topology and 11-dimensional triangles on our next episode. All right, I wanted to respond to some of your comments about our episode on the stochastic supertask. So first, we should acknowledge that we're not very good at arithmetic. There were 28 balls in the urn, which means you had a 1/28th chance of removing one, not 1/29th. There were not 29 balls. I got that wrong. Also, it should have said 9 times n in the formula, not 9 to the n. Arithmetic is hard, so is algebra. But here's something that we are pretty good at: infinite series. So I just wanted to clarify, because it came up a lot in the comments, that you guys are right that 0 times infinity is undefined. But 0 plus 0 plus 0 plus 0 plus 0 infinitely many times is defined to be 0. We define an infinite sum like that to be the limit of the partial sums. So you add a few zeros, and then you add a few more zeros, and then you add a few more zeros, and you see what's happening to that. And that just stays 0. The limit of that is 0. So 0 plus 0 plus 0 plus 0 plus 0, and so on, is 0. I liked Vrishkanen's comment that, am I missing something here, or is the idea of a time restriction arbitrary here? Saying at noon seems like a roundabout way of letting n tend to infinity, and would have the same result. That's a good response, and it's a good question. So we needed everything to happen in a finite amount of time in order for there to be an end. We were asking how many balls were in the urn at the end, so we needed everything to happen in a finite amount of time. So it was like letting n tend toward infinity, but we couldn't let time tend to infinity, because you can't really ask about what the urn is like at infinity. Good question. And finally, our challenge winner is Florence B. So Florence showed that there are infinitely many balls left in the urn at noon if you always remove the median number 1. Their proof is really great. Go check it out in the comments. See you next week.